Hi, today I want to talk with you about the following scenario or experiment in which you toss a die 3 times and record the number of times it lands on a 4. So there's a few things about this setup that I'd like to talk about. So each trial or toss of the die has one of two outcomes. Either the die lands on a 4 or it doesn't. The more general scenario that describes this is success or failure. In this instance, the probability of success on each trial or toss of the die is 1/6. Because it's a 6-sided die, and there's only one way in which it can land on a 4, so 1/6. The probability of failure is 5/6. There's 5 outcomes which corresponds to not a 4 out of 6. Now each toss of the coin is independent, that is, one toss of the coin does not affect the next. And there's a fixed number of trials, which in this case is n equal to 3 tosses of the die. One more very important piece is that here we're defining the random variable x to be the number of successes, or 4s, out of 3 tosses, or 3 trials. The question here is, what is the probability x equals 2? Well, probability x equals 2 can happen in 3 ways. Those 3 ways are illustrated here in red. Here's the first way. The first is success, the second is success, the third is failure. Or the first is success, the second is failure, the third is success. And then the last way is failure and then followed by 2 successes. So those are the 3 ways in which x equals 2 can occur. I'm going to come back to the number of ways in which this can occur later. For now, I want to continue with this calculation of probability. Notice that we have a keyword here. That keyword is or. Because these are disjoint, we can just add the probabilities. Why are they disjoint? Well, for example, the first outcome and the second outcome has the third outcome being a failure, while the second way in which this occurs has the third outcome being success. Those two cannot occur at the same time, so they're disjoint, and we can add. Okay. Now, of course, you have to apply this disjoint property to each of the outcomes. So let's calculate this probability here. I'm going to copy that. My apologies. I'm going to paste that here. Not sure why it's not. Let me try this one more time, and then I'll write it out the long way. There it is. Okay. So my apologies, I was just being a little bit lazy here. And let's move that here. So it just saved me some writing there, and I apologize for you having to deal with this. So this is equal to probability of this outcome. Now I'm going to erase the OR event here, and because we discussed the ORs are disjoint, I'm going to take probability of each of these and add them. Now, the probability of each of these can be calculated with these ands here. That's a key word. Because the tosses of the die are independent, this is going to be probability of success times probability of success times probability of failure. Now, the second one is going to have two probability of successes. Now, because they're in slightly different order, it doesn't matter because they're being multiplied. So I'll just do P of S squared times probability of failure. And the last outcome, despite that it's failure, success, success, that's still probability of success squared times probability of failure. I can write this as just 3 times probability of success P squared times 1 minus P, probability of failure. I could do Q instead of 1 minus P, but let's just leave that. And if I wanted to, I can put in the probabilities. This will be 3 times 1/6 squared times by 5/6. And we can work out what this is. And we just need to calculate it. And we will get 0.069. So about 7% chance of this happening. Okay. Now, let me just discuss each of these items a little bit more generally. So in general, with N trials, and the same assumptions as above, that is, these assumptions. So if we have all of that in N trials, then the probability of having K successes, well, that would be P. I'm going to work backwards here. Here it was to the exponent of 2. That corresponded to 2 successes. K has the role of 2 here, so that will be P to the K. 1 minus P, remember we have N trials. If K of them are successes, that means that the rest, being N minus K, need to be failures. What about this 3 here? Why is there 3? Well, that's because this event could occur of 2 successes. It could occur in 3 ways. Well, why was that? Our random variable here, x, is the number of successes out of 3 tosses. In general, it will be the number of successes out of n tosses. So here, this 3 is the number of ways to select 2 successes out of 3 tosses. So that's going to be 3 choose 2. Why is it 3 choose 2? Well, our random variable only cares that we have k successes or x successes out of n tosses. It doesn't care about the order. I wrote out the order in which it could occur, but the random variable is just that I have x successes out of 3 tosses. So it actually doesn't care. So this will be n choose k, or, n choose x, depending on your random variable. Here I said x is k, so it'll be n choose k here in this formula. If you were to write this as probability x equals little x, as the book does, this will be n choose x times p to the x times by 1 minus p to the n minus x. And whichever one you choose, this is just replacing a variable. This is the general binomial distribution formula. So it's the general binomial probability distribution. Okay, so that is a motivating example of how we arrive at the binomial probability distribution formula. Thank you.